Hello my dears, how are you all? So I think in the last class itself we finished the control system. So as far as the examination point of view, I did more than enough. Okay, if you watched all the videos regarding the control system, definitely your level will be certain. Before, if you watch, that means the videos or your level before watching the video definitely will be changed. Definitely will be changed at least by 1 degree. That I can confirm. At least by 1 degree your level will be higher. That I can confirm. Because that much quality classes was there, that much quality notes that I have given to you. So please follow this. Please watch this. And the last session of Bode plot and all, that are very high level examination only. That type of question will come, the slope, regarding slope and all. But except that, all we discussed in your syllabus, according to your syllabus. And I already told you, it is actually there is some more syllabus, some more part is there, not in your syllabus but in control system. For example, controllability and observability, and the state to transmission metrics and all, right? It is very big problem actually. So that is not included in your syllabus. That's why I skipped. But if time permits, if you get enough time, I will come back and I will tell. Okay. And one more thing, the root locus now. But the theory and the problem regarding root locus is very big and very vast. So as far as the competitive examination point of view, I hadn't seen any question regarding root locus yet now. Okay, so today we are going to discuss some important topics that already I have left in circuit theory. So what I did, under the heading of circuit theory, I covered basic electrical and circuit theory, as well as the magnetism. Some part of magnetism also I covered, but I have left some topic there, but it is in your syllabus, so I am going to complete that topic now, and after that we will move to power system. Okay, so this is not under the control system. Okay, this is not under the control system, my dear. So just I'm going to rub it because it's not under the control system, it's under the circuit theory. Okay, so I will put these videos on the playlist of our circuit theory. Okay, so this will come under the session of circuit theory, that was magnetic circuits. Magnetic circuits. Magnetic circuits, my dear. So before we are going into magnetic circuit, what is, you know, the magnetism and all, we are not your 10th standard or plus 2 student, you are engineers, of course, you know the basics. You don't want to much more into the history and geography of magnetism. So let's see some basic terms and we can continue with the basic terms. Okay, we can continue our classes with some basic terms regarding the magnetism ideas. And first one is magnetic field. Magnetic field. What do you mean by the term magnetic field? Magnetic field is nothing but, my dears, the space around a magnet is called the magnetic field. So it's a simple definition. Magnetic field is nothing but space around a magnet is called, my dears, magnetic field. Space around a magnet is called the region around the magnet is called the magnetic field. Next, magnetic field lines. Magnetic field lines. So magnetic field lines is nothing but, magnetic field line is nothing but, it is an imaginary line. Imaginary lines used to represent magnetic flux. You to represent magnetic flux is called the magnetic lines, field lines. It starts from North Pole and ends in South Pole. You already learned this. You already know this, right? No need to move much deeper because you already know this. Okay. So that is the magnetic field lines, and there are so many properties of magnetic field lines, my dear, that you already know, and I will say one by one. First one, it never intercept each other. Magnetic field lines is nothing but, I'll just examine it. This is the magnet. Suppose this is north and this is south. So this is nothing but the magnetic field. This is nothing but the magnetic field. And it never intercept each other. It never intercept each other. It always make a parallelism. It is always move in parallel. It never intercept each other. It may be contract or expand at certain points. Suppose this point, its density may expand, its density may increase, but it never cross or it never intercept each other. It never intercept each other. It starts from North Pole to South Pole, North Pole to, and start from North Pole and ends in South Pole, external to the magnet. And start from, or simply and South Pole to North Pole. Inside the magnet. What I wrote, my dears. So it is external to the magnetic field. It is external to the magnet. It starts from the north and ends in South Pole. But inside the magnet, it starts from north, south, and its end in south. Its end in north. It starts from south and it ends in North Pole. That is very, very important. Okay, so external to the magnet, if you draw some magnetic field lines, it starts from north and ends in south, but inside it is from south to north. The direction of magnetic flux at a particular point is the tangential to the magnetic field lines at that point, which means nothing but, if you want to find the direction of this point, means you simply draw the tangential here. That is the direction of the magnetic flux. That is the direction of the magnet. Because in certain analysis, my dear, suppose there are North Pole and South Pole. You already learned this regarding DC machines. So it is, you draw like this now. You draw like this. So this is the direction of the magnetic field from North Pole to South Pole, external to the magnet and all. So the curved lines now, it doesn't make any sense when we are dealing with the magnetic circuits. So exactly we need a certain definite direction to the magnetic flux. For getting the definite direction of the magnetic flux at any point, just to draw the tangent at that line of force region, you will get the what? Magnetic flux direction at that point. Is it clear, my dear? So these are the very important points. It never intercept each other and start from North Pole to South Pole, and the direction of the magnetic flux is always tangential to the direction at that point, tangential to the direction of at that point. And it always acts like structured elastic thread and try to shorten themselves. See, this is very what a super definition of magnetic, a super property of magnetic lines of force, my dear. It is always act like a structured elastic thread. It is not simply, it is like a structured elastic thread, and it is always try to shorten themselves, means it always try to shrink towards the magnet. Even though if you draw this magnetic lines of force is far from the magnetic field or the magnet, actually this lines of force is trying to do what? It is trying to come closer to the magnet. It's trying to come closer to the magnet. That is why the curved surface. That is why the curved surface. And you have to observe a beautiful thing here, my dear. You have to observe a beautiful thing here. Always this forms a circular path. Magnetic lines of force always form a circular path. Try to form a circular path, but unfortunately that won't happen. But it always try to form a circular path. Why? Because the property of the magnetic flux line is that it always try to shorten themselves. It always try to shorten themselves. The shortest area of a figure is nothing but its circular form. What is the least area figure means? It is a circle. What is the least area three-dimensional object means? It's a sphere. That is why water bubble always form in the form of a spherical shape, because it is the least area in order to reduce the surface tension. Okay, so that is another point you can add. Okay, so that's all about the properties of magnetic lines of force. Okay, my dears, next, magnetic flux. Represented by phi. Symbol is phi. Magnetic flux is nothing but, my dear, total number of lines of force in a particular region. Total number of lines of force in a particular region is called the magnetic flux. For example, simply I got some irregular shape and I want to calculate the magnetic flux here means simply count the number of turns which is passing through this area. That's all. That is the magnetic flux. And its unit is nothing but, my dear, very, very important. Unit is nothing but Weber. Unit is nothing but Weber. And 1 Weber will be equal to 10 raised to 8 Maxwell. That also you have to note. 1 Weber is equal to 10 raised to 8 Maxwell. Maxwell is the another unit of magnetic flux. Okay, that connection is 1 Weber is equal to 10 raised to 8 Maxwell. This just to remember this. Okay, and flux density represented by a symbol B. It is nothing but, my dear, flux per unit area perpendicular to the direction of flux line is called flux density. Is called a flux density. I will tell you what it is. Normally, generally, if you ask someone what is the flux density means, flux density is represented by B is equal to phi by A. But you have to add one more line, then only this is exactly correct. That line is nothing but perpendicular to the direction of flux line. Flux density is simply not flux by area, my dear. But suppose this is the direction of magnetic lines of force. Suppose I want to measure the flux density of my palm. Suppose I want to measure the flux density of my palm. I can't place my palm like this. I can't place my palm like this. But I should face my palm exactly perpendicular to the direction of the magnetic flux line. Then only the flux density is correct. Flux density is correct. My dears, flux density means, suppose this is the region of our concern. Flux density means flux per unit area. If my palm slightly tilted, some flux will be passed like this, which cannot touch this palm. Suppose I turn my palm like this, and after that I measure flux density. Suppose only few number of lines of force will link with my palm. So I cannot get exact flux density. So always flux density is nothing but flux per unit area, and that area should be perpendicular to the direction of the magnetic field. Very, very important. Very, very important. Very, very important. Always perpendicular to the direction of the magnetic flux. Magnetic flux. Or magnetic lines of force. Or magnetic lines of force. Its unit will be nothing but, my dear, unit is nothing but Weber per meter square or Tesla. Weber per meter square or Tesla. Weber per meter square or Tesla. Is it clear, my dears? Is it clear? Can I rub this? These all are definitions. You should learn this. Okay. Maybe one word question may ask from this area also. Okay. Because it's in your syllabus. That's why it's more important. Next, permeability. Represented by a symbol mu. Represented by a symbol mu. Permeability is similar to conductivity in electric field. This is also a question. This is also a question, my dear. Permeability is similar to conductivity in electric field. Conductivity in electric field. That means it is nothing but, my dear, it is the ability to conduct magnetic flux through it. What, my dears? It is the ability of a material to conduct a magnetic flux through it. For example, according to the permeability, according to the permeability, materials are again classified. That I will tell you. Paramagnetic, diamagnetic, and ferromagnetic. So first of all, we will start with the diamagnetic. Diamagnetic means it is a material. Suppose you place a material in a magnetic field, my dear. Say rubber. Then it will not conduct any magnetic lines of force, or very feeble lines of force will be carried. So the lines of force will be move like this. It will not conduct any magnetic lines of force. The magnetic lines of force move away from the material. That is nothing but what I say. It will not carry, it will not carry any magnetic flux through it. Any magnetic flux through it is called the diamagnetic material. Diamagnetic material. Okay, it will not carry any magnetic material through it, and it is called diamagnetic material. And the value of mu will be less than 1 always. Less than 1 always. When come to paramagnetism, paramagnetic means it is feebly what I say. It is completely repel, my dear. It is completely repel, but it is feebly attracted to the magnetic lines of force. Suppose you applied 10 lines magnetic lines of force here, then at least two of them will come to here and rest of them will move away. That means its permeability or ability to conduct, I can say that slightly greater than 1. Slightly greater than 1. Compared to the ferromagnetic material, my dear, suppose this is a ferromagnetic material, say iron. Iron is a ferromagnetic material. Suppose iron is a ferromagnetic material. If you place iron here, my dear, suppose this is the magnetic lines of force supposed to flow, but if it a ferromagnetism means it will come closer and closer and it will move to the or move inside the magnetic material, and the flux density inside is very high, so that its permeability, I can say that very greater than 1. Very greater than 1. So accordingly you can classify material. Okay, this actually it's not the scope of our syllabus, but for your information I told you. For electrical terms of view, just remember this, my dear. Permeability is nothing but ability to conduct magnetic material. Okay, so diamagnetic means completely repel, paramagnetic means feebly attract, and ferromagnetic means complete attracted, full and attracted. Okay, that's a diamagnetic, ferromagnetic and paramagnetic material. Okay, and so it is similar to the what? Conductivity in the electric circuit. Similar to conductivity in electric circuit. Okay. Next definition is, and also the unit, my dear. The unit is nothing but Henry per meter. Unit is nothing but Henry per meter. That also you have to remember. And permeability of air. Permeability of air equal to mu 0, which is nothing but, my dear, 4 pi into 10 raised to minus 7 Henry per meter. This also you have to remember, because air is also a conductor of magnetic lines. Even though air is a poor conductor of electricity, but air is a very good conductor of magnetic lines. So it also having certain permeability, and that permeability is nothing but 4 pi into 10 raised to minus 7 Henry per meter. Is it clear, my dear? Is it clear to you? Is it clear to you? Next, relative permeability. Represented by a letter mu r. Represented by a symbol mu r, my dear. Relative permeability is nothing but mu r is equal to permeability of material divided by permeability of vacuum or air. Vacuum or air, which is nothing but material, it is simply mu, and for vacuum it is nothing but mu 0. So mu r is equal to mu divided by mu 0, or simply mu is equal to mu 0 mu 0. Or there is another definition for the relative permeability, my dear. It is nothing but flux density in the material divided by flux density in air, which is nothing but B material divided by BA. So what is B? Already told you, flux density. So B material is nothing but, there is a definition of B, there is a relationship between B and permeability is nothing but, my dear, B is equal to mu into H divided by mu 0 into H. And this definition is one more thing you have to add for same magnetic field intensity. For same magnetic field intensity. So this H and H got cancelled, simply mu divided by mu 0. So mu r is equal to mu divided by mu 0. Because magnetic flux density same means H and H are same, so it can be cancelled. This is another definition for relative permeability value. Another relation for relative permeability. And its unit will be, I already told you, relative permeability is a unitless quantity. Relative permeability is a unitless quantity, my dear, unitless quantity. Okay, next, magnetic field density represented by letter H. H is nothing but, my dear, mmf per unit length. So simply mmf for length, which is nothing but mmf. So you have to know the word of mmf, right? Magneto-motive force you have to know, right? So next definition I will tell here itself. Magneto-motive force. It is nothing but the force required to set up flux, and mmf is nothing but, my dear, represented by n into I. mmf is nothing but n into I, and it is nothing but similar to EMF, my dear. mmf is nothing but similar to EMF. What is EMF? It is a force required to set up a current through the circuit. Similarly, it is a force required to set up a flux through the magnetic circuit. That's all. That's called a M. And it is nothing but n into I. N into I. So H will be equal to n into I divided by L. N into I divided by L. Unit will be nothing but, my dear, ampere turns per meter. I ampere, n turns, so ampere turns per meter. That is the unit of what? mmf, my dear. That is the unit of mmf. That is the unit of mmf. Okay. And one more connection you have to write. B equal to mu 0 mu r into H. It's very, very important relation. B is equal to mu 0 mu r into H. And H is a vector quantity, my dear. H is a vector quantity. H is a vector quantity. That also you have to know. Okay? Is it clear? Is it clear, my dears? Is there any doubt? It's very, very simple topic actually. We completed control system now. So compared to that, it's nothing. Compared to control system and what we discussed very, very, very hard things we discussed, and we break the hard things, right? So it's nothing. It's very, very easy. Okay. Just a theory you can expect from this, and small problem which connecting B, mu, 0, H, N, that like problems also you can expect. Small problems. Okay. Next. Comparison between. This already you have been taught in first year, right? So let's first take the similarities. Then we will go for the dissimilarities. Okay, first similarities. I will write like this. Electric circuit. I will write here magnetic circuit. You also make two columns like this, my dear, because many confusing terms will be there. You have to note it. Okay. First thing is nothing but here the current is set up here now. Similar that there it will be flux phi. Current is equal to I. And second similarity, here it is EMF and here it is what? MMF. And third one, resistance R is equal to rho L by A. Resistance R is equal to rho L by A, that too in ohm. The same parameter here is nothing but, my dear, reluctance. So reluctance is nothing but, it is the opposition made by the magnetic circuit to the magnetic lines of force, similar to the resistance in the electric circuit. So resistance in electric circuit is nothing but, it is a resistance offered by the conductor or the element which is connected to the current flow. So similarly, reluctance is nothing but, there is an opposition offered by the material to the magnetic flux or magnetic circuit. It is an opposition made by the magnetic circuit to the flux lines of force, right? So that's called reluctance. It is nothing but L divided by mu 0 mu r into A. L divided by mu 0 mu r into A. Capital A also you can write, no issue. Where A is the area of cross section and L is the length of the magnetic circuit. I will write it here. Length of magnetic circuit, meter, area of cross section of magnetic circuit in meter square. And fourth one, resistance equal to R equal to V by N, EMF divided by current. Same manner here, reluctance MMF by flux. Very, very important relation, that is. Very, very important similarity, my dear. And next, resistivity equal to 1 by conductivity, or 1 by rho. Am I right? 1 by rho. Similarly, here reluctivity is nothing but 1 by permeability. It's equal to 1 by mu. It's equal to 1 by mu. Next similarity is nothing but conductance. G is equal to 1 by resistance. Here susceptance, sorry, conductance, now it is permeance, 1 divided by reluctance, 1 divided by reluctance. Okay, and the unit of resistance, reluctance is nothing but Weber per ampere turn per Weber. This is very, very important, my dear. Reluctance unit is nothing but MMF. MMF is ampere turn divided by flux is nothing but Weber. So ampere turn per Weber will be the unit. Ampere turn per Weber will be the unit. Next, total EMF in series circuit equal to I into R1 plus I into R2 plus I into R3, etc. Similarly, total MMF in series magnetic circuit equal to MMF N into I na, so N1 into I plus N2 into I plus N3 into I, etc. Or you can say like that, phi into S1 plus phi into S2, etc. That also same, because current is same, similar current is same for MMF magnetic circuit. So phi into S1 plus phi into etc, etc. So phi is same, similar to phi is same, because from here MMF is nothing but reluctance into phi, S into phi, correct na? So that's why phi into S1 plus phi into etc up to phi into S. So these are the very, very important similarity of electric and magnetic circuit, my dear. So let's go for the dissimilarities. Dissimilarities. First similarities, dissimilarity is nothing but there are very good insulators for current in electric circuit to the flow or simply in electric circuit. But in magnetic circuit, there is no perfect insulator. That means always have some leakage flux. Very, very important, my dear. So in electric circuit now, we have so many insulator. For example, this is a wire, my dear, this is the wire. So this is the insulator. That means the wire is wound above with an insulator so that the current can be confined to the certain direction, confined to flow in a certain direction. But in magnetic circuit, unfortunately, there are no perfect insulator for magnetism or magnetic circuit. Even though if you tightly closed a magnetic material with some magnetic insulators, there is always some leakage flux. There is always some leakage flux. Very, very important dissimilarity between electric and magnetic circuit, my dear. Now you write dissimilarities again. Now you write dissimilarities. And next dissimilarity is not. Energy is required as long as the current flows. But in magnetic circuit, energy is required to set up flux, but not to maintain it. What is the meaning of this word, my dear, this sentence? See, in an electric circuit, when the EMF is switched off, my dears, what happened? The current will be zero. The current will not be there. But in the case of a permanent magnet, you assume in the case of a permanent magnet, in the radios and in speakers, the back side will be a permanent magnet, right? In the case of a permanent magnet, once it is energized, it will long last. It will last for a very long time. That means the energy is required only for start up a flux in it, but not for maintain that. It will exist for a very long time. But in the case of an electric circuit, my dear, even if you switch off the EMF, that means at the time, not even if, at the time itself you switch off the EMF, there will not be any current flow. The current will what? Cease immediately. The current will cease immediately. The current will cease or stop immediately. Okay? Okay? And air is very good insulator for current, but not a good insulator for flux. That means it's a, or air is a good conductor of flux. Air is a very good conductor of flux, my dear. That is there is the controversy between electric and magnetic circuit lines. See, the air doesn't carry any electricity, right? You know, only under very stressed condition, suppose 30 kilowatt per centimeter, peak to peak, or 21.2 kilowatt per centimeter RMS value. Only at that range of stress, the current will be flow through the air. But unless or before that range, air is a perfect insulator for current. But in the case of a magnetic field, my dear, the magnetism is different from electricity or electricity. The magnetic flux lines can easily flow through the air, easily flow through the air. That means the air is a very good conductor for magnetic flux. Air is a very good conductor for magnetic flux. Those that are the what comparison between electric and magnetic circuit. And one more you can write: saturation can be there in magnetism, but not in electric field. That means saturation is nothing but, my dear, suppose you took a material, if you continuously flowing flux lines through it, after a certain region, the core or the material got saturated, means suppose it carries 100 lines of force now. Even if you pass thousands of lines of force through this, it only carries 100. It will not carry more than 100. That means there is a saturation point. There is a capacity of magnetic material to conduct a flux through it, conduct a flux on or through that material. There is a capacity. Even if after that you have thousands of lines of force in your hand, if you simply spread it, it won't conduct. It only conduct 1000 lines of force. Array bus, I can't. That will be the reaction of the material. So that is called the saturation process in magnetism. But in an electric field, there is no saturation at all. If you the current carries by a conductor will be there, always be there for certain limit. But after that, the conductor will be burned. That is not called the saturation. It is simply the vanishing, not the saturation. Here the saturation also it can carry 100, but there the burnout process means the current will be 0. It can't conduct anymore. So that is the difference. That is the difference. So these are the dissimilarities between electric and magnetic circuit, my dear. This is very, very important table. I think you already studied in first year, right? Basic electrical you studied, I think. Okay. Okay. Is it clear, my dear? Is there is any doubt, you can ask. Is there is any doubt, you can ask. Okay. Next, can we do a problem? In series magnetic field, can we do a problem? Just a minute, my dear. I will refill my pen. Okay, just a minute. Okay, can we do a problem? The magnetic frame shown in the figure The magnetic frame shown in the figure is made up of iron. Iron has cross section 3 centimeter on each side. Air gap 2 mm, and each of carries 1000 turns each. Excitation current of under the excitation current of 1 ampere. The relative permeability of part A and part B are 1000 and 1 to 1000 respectively. Find A complete reluctance of or total reluctance. Total reluctance of complete magnetic circuit. B total mm of C flux, and D flux density. Through the figure, my dear, I will tell that later. Okay, can we do this? Can we do this, my dear? For that, I am going to rub the top session, because I have to write something now. That's why. I think you already note it down. It's a very big question, but It will not be asked completely, but a part will be asked so that we can easily answer. First one we have to find what, my dear? The reluctance of the complete part you have to calculate, right? So let's do the reluctance of part A. Part A. So we have the equation for reluctance of part A is that LA divided by, this A stands for length of A part, mu 0 mu r into A, where this A is nothing but the cross section. Better you simply omit this A. So L divided by mu 0 mu r into A is the equation for the reluctance, my dear. So what is L here? I already told you L is nothing but it is the length of the magnetic circuit, or the length of the flux, or the length of the magnetic lines of force. You remember one thing, whether the magnetic circuit is in circular cross section, rectangular cross section, triangular cross section, or square cross section, the flux is always flows in midway of the structure. See, in midway of the structure only the flux will flow. That is very, very important thing you have to note. Very, very important. So it is already given that each side consists of 3 centimeter, means each side, the cross section, they gave the idea of a cross section. They gave the idea of a cross section of the material, and each side 3 centimeter means this is 3, this is 3, this is 3. What is the structure? It is a square. It is a square. That you have to note. And length of the magnetic circuit is nothing but, L is nothing but, see the part A, here to here length only we can calculate, we have to know. The total length is nothing but 20, but this length is 3 now, total here to here is 3 now. So here to here will be 1.5 and here to here will be 1.5. Am I right? So the L will be nothing but, my dear, 20, I can say here, L will be nothing but 20 minus 1.5 plus 1.5. Total 20, here to here it is 20, but you have to subtract this and this. This will be 1.5, this will be 1.5. This will be 1.5, this will be 1.5. So 20 minus 1.5 minus 1.5 is nothing but, my dear, 70. So substituting this, it is nothing but 17 into 10 raised to minus 2 divided by 4 pi into 10 raised to minus 7 into mu r is given by part A is 1000 into A. Area of cross section is nothing but, for square it is nothing but A square. So 3 centimeter means 9 into 10 raised to minus 4. Simply substitute this, you will get. Simply substitute this, you will get. And the answer is nothing but, my dear, answer is nothing but 15 into 10 raised to 4 ampere turn per Weber. Am I right? Ampere turn per Weber. Okay, that's all about the reluctance of part A. Reluctance of part A. Can we do the reluctance of part B? Can we do the reluctance of part B? Can we do the reluctance of part B? Part B means this area. Yes, B will be equal to, similarly L divided by mu 0 mu r into A. So what is the length of part B, my dear? What is the length of part B? The total length from here to here. The total length. So from here to here we already know 17. From here to here it is 8.5 now. Total here to here it is 10. But minus this you have to subtract 10, 1.5. Similar manner here also, minus this you have to subtract. Minus this you have to subtract. So it will be 1.5 here and 1.5 there. So it will be total 10 minus 1.5 here, also 10 minus 1.5 here, plus 17 here. So it will be total, what L will be equal to what, my dear? I can write here L separately here. 10 minus 1.5 plus 10 minus 1.5 plus 17. So it is nothing but 8.5 plus 8.5 plus 17, simply 34 centimeter. So it will be 34 into 10 raised to minus 2 all divided by 4 pi into 10 raised to minus 7 into mu r is nothing but for part B 1200 I think. Area is nothing but 9 into 10 raised to minus 4. No change in that. So if you substitute, you will get 25 into 10 raised to minus 4 ampere turn per Weber. That's all about the part B. So part A and part B over. Is that everything over? No. Some reluctance also offered by the air gap also, because air is a good conductor. Air is a good conductor of magnetic flux, so there will be some resistance offered by the air gap. So what is the resistance offered by the air gap? So air gap reluctance. So we can write like air gap reluctance. It is nothing but Sg. Same manner Lg divided by mu0 mu r into A. What is the length of the air gap, my dear? 2 mm on both sides. It is given 2 mm on both sides means it will be 4 into 10 raised to minus 3 meter on total. 2 mm here and 2 mm here. 4 pi into 10 raised to minus 7 into air gap. Relative permeability of air gap is 1. I already told you mu r is equal to 1. Mu r is equal to 1 always. For air, relative permeability will be 1. So 1 into area is nothing but 9 into 10 raised to minus 4. So if you solve this, you will get 353 into 10 raised to 4. 353 into 10 raised to 4. Ampere turn per Weber. See, compare the permeability now. Compare the reluctance offered by the air. It is 353. It's huge reluctance, but there is still a magnetic lens of force will flow now. That's why. Is it clear, my dears? Is it clear? Okay. So complete will be what? Total will be. Total S will be equal to SA plus SP plus SG. So you will get, if you add 3, you will get 393 into 10 raised to 4. Ampere turn per Weber. That is the answer for part A. Total what? Reluctance of the complete circuit now. So this is the reluctance of the complete circuit. Is it clear, my dears? Is it clear? Now there is no need for remaining answers. Sorry. Next you have to see what is MMF now. Correct? B. MMF. MMF is nothing but, my dear, N into I. So how many number of turns are there? 1000 on one side and 1000 on another side with a current of 1. Correct now? With a current of 1. Correct? So it will be 2000 ampere turn. The unit is very, very important, my dear. Ampere turn. See. Next you have to find flux. How can we find flux? Flux is nothing but MMF by reluctance. Am I right? MMF by reluctance, correct? MMF you already have. Reluctance you already have. So your answer will be 5 into 10 raised to minus 4 Weber. Unit of flux is nothing but Weber. And D. Flux density. Flux density B is nothing but, my dear, 5 by A. 5 you have, A you have, so 5 by 9, 0.564. Number per meter square. So that's all about the question, my dear. So similar to the questions you can solve. Similar question you can solve. Okay. We will continue next on from tomorrow itself. Okay. By the next class we will continue the remaining session. So until then, bye. Take care.